Welcome to Will Fan Regulations Make My Fans Quieter? I'm Scott Arnold, Senior Manager of Publications and Standards for Air Movement and Control Association International. On behalf of our more than 400 members worldwide, I want to thank you for joining us. We realize there's a lot to see and do at the AHR Expo. We respect and value your time and hope you find this educational session worth your while. The information contained in the session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. Lastly, this session is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the material without written permission from AMCA International is prohibited. And with that out of the way, let's meet our presenters. Brandon Kudaquest is a senior consultant in architectural acoustics and noise control for Threshold Acoustics. His work includes projects at the Woodruff Arts Center in Atlanta, live music venue Steelhouse Omaha, Sacramento Memorial Auditorium, Gallaudet University, and the National Technical Institute for the Deaf. He is the Vice Chair of ASHRAE's Technical Committee on Sound and Vibration and Principal Investigator for ASHRAE Research Project 1919, which deals with the effects of duct size and aspect ratio on flow noise and elbows. He has presented to the Acoustical Society of America on topics including algorithms for duct flow noise, sound data for fan coil units, historical theater renovations, and the history of the ASHRAE Handbook. First, though, we'll be hearing from Rad Ganesh. Rad has over 37 years of experience in the air movement industry, the last 23 with Twin City Fan. For Twin City, he has performed numerous functions, including research and development, laboratory management, customer training, fan systems regulatory compliance, applications engineering, product development, and customer testing. Additionally, he has assisted sales and order acquisition and fulfillment. Prior to Twin City, he spent 11 years in product development with the Trane Company. He has presented for ASHRAE and AMCA International and conducted company training seminars around the world. He has served on numerous AMCA International technical committees and in 2019 received the AMCA Distinguished Service Award. Red?
Good morning. Everybody hear me okay? Welcome. Are you guys all awake? Okay, awesome. Thanks for coming. This is a very interesting topic, pretty current, and hopefully you'll all walk away with some knowledge on fan applications and how it impacts acoustics and how do we combine regulations, efficiency, cost. It's a bunch of variables that you try to optimize here, right? So I'll just step through it. I'll do the initial efficiency, regulations, that part of it, and then Brandon will do the acoustics part. I think that slide on Brandon is a little bit out of context here because he was voted as the chair, not the vice chair of TC 2.6 yesterday. Yeah. So let's give him a round of applause on
thanks.
Brandon being now the chair of TC 2.6. So, learning objectives. Energy efficiency today is more important than ever. What is the industry doing today? How are energy efficiency and fan noise related? You know, there's a correlation there between efficiency and noise. I'll talk about that a little bit. Can quiet fans be selected based on energy efficiency alone? That's a key point we are going to discuss. And every fan selection is different and important. How do we compromise and optimize cost, efficiency, noise, and regulations? That's the whole idea here, to bring it all together. So these are the questions. So if you want your PDH hours or whatever, you know, there's going to be a Q&A session at the end, and I will decide who is a pass or a fail, right?
Yes, yeah.
Okay. Sounds good. Okay, so this is the abstract for this session. Fan efficiency metrics are receiving significant attention in the wake of the DOE fan regulation. These do not address noise specifically. This is intended to provide an overview, and we are going to introduce the fan energy index, how we came to that metric of 1, and any other constant that could be used in the future. And also, high FEI is not a guarantor of quiet operation, and we'll talk about that a little bit too. So let's talk about energy, right? Fans, you walk around in the show, every equipment has a fan in it, right? Every one of them. unless it's some workshop tool like a miter saw or a shear or a machinery, every heating, ventilating, cooling equipment has a fan in it, right? So the US energy consumption, you can see the pie chart here. 34% is commercial and industrial, 22% residential, and 26% transportation. This is from the US Energy Information Administration. It's a little bit old, but 51% of the total US energy used is by commercial and industrial fans. So as you can see, in 2020, US energy consumption was 27 trillion kilowatt hours, just to give you an idea, out of which 7.6% or 2 trillion kilowatt hours is consumed by fans. And with 1% reduction in energy, you can save enough to power 26 million households in the United States. So that's staggering, right? So that's why Big Brother DOE is coming after our industry, and it is going to happen. It goes into an active mode, then it goes into a passive mode. Eventually, it will kick into high gear, and there is a lot of interaction going on between the industry and the DOE, Department of Energy, for those of you who don't know what DOE is. So it's coming. Indoor air quality, you can see that this is pretty, the amount of time spent indoors is 87% by all of us human beings, right? And that is pretty staggering. So you need to have good indoor air quality. 90% of our lives are spent indoors and so on. Only 7.6% of the people spend their time outdoors. That's horrible. I mean, you would like more and more people to go outside and get the fresh air. But that's what it is, You try to encourage kids to go out and play, and those days seem to be gone. Everybody wants to sit and do this, and it's that has to change. And you got to lead. If you take care of these, then hopefully the lifestyle of people, the environment, the whole humanity would improve in general. So again, health, big time, right? So if you have some of the real consequences of poor indoor air quality includes the increase in asthma, where we spend about $5 billion a year. Allergens, 9.7. That should be $billion, sorry. It's not $9.7 per year. Asthma Allergy Foundation of America said in 2021. There is a lot of environmental issues dealing with the World Health Organization. Dangerous indoor air quality and sick building are a growing area of law for lawyers in the areas of personal injury, real estate, construction, homeowners, and associations. So it's a big deal. Indoor air quality, indoor environmental quality, they're all a big deal. Environmental quality, just add noise and vibration to it, then you get the whole picture. That is indoor environmental quality. So I'm going to play a short video on, this is rather old, from AMCA, and I would like to thank AMCA staff for bringing us together. Sorry about not mentioning AMCA here, my apologies. This is wonderful that we continue to do this. So we can just play this, right?
Yeah, if you just hover your mouse over the...
Reducing energy costs and extending system life are critical issues in commercial and industrial air systems. To help make fan system sizing more accurate and resourceful, AMCA International and its members have engineered a new metric called Fan Energy Index, or FEI. The FEI replaces the Fan Efficiency Grade, or FEG, that has been used for rating and regulating fan efficiency in the United States and Asia since 2010. FEG is a single-point metric that considers only a bare shaft fan's power at peak total efficiency. FEG ratings apply to a fan series across all of its impeller sizes, and the FEG rating does not equate to the fan's actual efficiency. Therefore, a sizing and selection window is needed to nudge impeller diameters to larger sizing. For greater optimization of fan system energy usage, FEI considers fans, motors, and drives in part load and full load conditions. And FEI ratings calculate the full range of airflow and pressure operating points instead of only at peak total efficiency. Engineers can now choose a fan with the highest FEI and expect top performance.
Okay, how many of you have heard of FEI? Hands higher? That's great, at least half the room. How many of you use it? Anybody? Okay, a few. Other than manufacturers, consultants, owners, operators, how many of you use it? Nobody, right? So this is an awareness issue, and we as fan manufacturers and through AMCA, we are trying to promote this as much as we can, because as I'll show you, fan energy index is an application independent metric. All that you need to know is your fan duty point and the FEI. It'll tell you, you don't need to know whether it's a centrifugal fan or an axial fan or anything. The FEI metric gives you a good feel for your application. Unlike whether you really need to know an efficient centrifugal or an axial, an FEI of 1 will tell you, okay, in your system like this, if you have an FEI of, I'm just throwing out a number, 1 or greater, you're doing good. And I'll talk a little bit more about the DOE also choosing this metric, and the state of California has made it mandatory in the energy conservation standard. So if you don't know anything about it, there is a plethora of information out in the AMCA website. Contact your manufacturers. They need to know this. It's very important, because if you don't comply, the fines can be pretty hefty. So I'll talk about that a little bit. Total efficiency of a fan is a ratio of the air power, which is generally total pressure times the flow rate in CFM divided by the brake horsepower and a constant. So this is the total efficiency of a fan. I'll get, if you have static pressure, then you define it as a static efficiency. There is a fundamental difference between total efficiency and static efficiency, because static efficiency, static pressure plus the velocity pressure or the dynamic pressure is the total pressure, right? So the efficiency is very important to be defined as to what the pressure is, and that's what is needs to be one of the important things to be taken away here. So the FEI index is a ratio of the output air power, flow times pressure is power, so this air power to the electric input power, into the VFD, through a motor, through the transmission, to the fan shaft, and the air out. If you don't have a belt drive and you have a direct drive, then the motor is directly coupled to the impeller. So the transmission losses go away, right? So the direct drive efficiencies are in general better than those with a belt drive, because the belt losses are excluded in the direct drive. So hence, the FEI is a complete wire-to-air metric. You put in the energy coming in, you look at the energy coming in, you look at the energy going out. It's a ratio of, I'll get into this, but it is a complete wire-to-air metric. Okay. Next, we move on to the definition of FEI. What is FEI and how is it defined? FEI is, first of all, fan energy index. Just like you have the regulated pump energy index, you have the compressor energy index, likewise we have the fan energy index. But unlike the pump energy index, fan energy index is based more on the application, whereas the pump energy index is based on the product. So you have to worry about whether it's a centrifugal pump or a submersible pump, whereas in fans you don't really need to know about a type of fan if you follow the FEI metric, because it's application dependent. Why is that? So the ratio of FEI is the reference fan electric input power, and I'll talk about this reference fan a little bit, divided by the electric input power of the actual fan that you select. Okay, it's all the way from, the shaft to the electric input power in kilowatts. reference and rated electric input power are calculated at the same duty point or point of rating of airflow and pressure. So when you select a fan, what do you generally need to know? You need to know the flow, the static pressure or the total pressure, and where it is. Like you need to know the density. That's all you need to know to select a fan. You don't need to know anything else. And from that input, we have to tell you what is the right fan for your application, right? So this reference fan is basically a math equation. It's called the virtual fan power, and it's also a function of the airflow rate times the pressure. If you want to know more details about that equation, you can go to our AMCA standard 208, which will give you how the background of why you have this reference fan. So as I said, FEI is a true application-based metric, and it's not a product-based metric. Like FEG, it optimizes system design with proper fan selection and save energy. By the way, feel free to ask questions. I like interaction, so if you have any questions, if it goes out for too long, I might have to push it out until the end, but if you can raise your hand and want to ask a question, feel free to do so. Generally, a higher FEI means lower fan energy or power consumption for the same duty point. That's what it is. And why is it important for system designers, right? If you look at the total pressure of a ducted system, power divided by airflow is total pressure, right? So what does that tell you? You really need to have low pressure duct systems to have energy conservation. But where do you have to fight it? In order to have low pressure duct systems, you can't have abrupt transitions. You have to have gradual transitions, and hence there is always a fight going on between space and having a good duct system design, right? You can't have elbows. You can't have a flex duct being scrunched around everywhere. All that is leading to pressure drop, and to overcome that pressure, you will have to consume more power. So there is a compromise where you really have to have good total pressure design systems and just not waste away energy. Yes, sir.
I've experienced that even the customer does not know exactly the point of operation. So how can they judge about the FEI? This is my first question. Then in some applications, like if you have a dust filter or something like this, the pressure is not stable or is not constant.
Mm-hmm.
So it's
moving. The system,
moving, yeah.
the
So
system curve is moving.
what do you take into consideration?
Right. So first of all, as a consulting engineer, they have to know the duct design systems, and they have to specify what is needed for the fan selection. The customer may not know. That's why you have consulting engineers who would do the calculations on the duct system, not only the pressure and the flow requirement based on how many windows you have, how much outdoor area you're bringing in, etc. So that's in general their responsibility. Fan engineers, we can help them in that process. And Brandon can speak more to that too when he comes on from that perspective. Mm-hmm. How do you know? There is a mechanism. The mechanical engineer on the job will specify that. The other thing is, as you said, as filters get dirty, the system resistance goes up and down the fan curve. So generally, if you have a process fan, right? If you have a process, it's got one load, one duty point, and you do that. But if you have a variable air volume system or a variable load system, you have to accept a range. And the fan energy index will let you operate in that range, and I'll show you that map in a second. So the second question can be easily answered. You can decide as a consulting engineer, or even we can advise our customers as to what is the range you need to operate your fan at in your selection, and we'll talk about that. Does that help?
Thank you.
Okay. Good question. So if you look at if we talked about the FEI, right? So you can have for example, in the state of California right now, the fan energy index needs to be greater than or equal to 1. They picked that. And it is a good metric because we as the industry through AMCA, did a lot of analysis on how many fans are sold, what are the power, how many types, etc., etc. So we came up with this one to be a reasonable level for regulators to follow. And when that happened, you can easily, it's a simple metric. FEI greater than 1 is compliant. If it's less than 1, it's not compliant. And there is a compliant range, as we talked about in the fan. So you can get this range from peak pressure down to a certain percent wide open volume. This is the volume, so a certain percentage below that. And in this range, you can see that the fan energy index is 1. So this is the fan energy index right here, and anything over 1 is that compliance range. So you take a simple fan curve and you can tell that, right? All right, now you have certain deficiencies in this fan map between high efficiency fans and low efficiency fans. For example, if you look at these, on the x-axis again is airflow, y-axis is static pressure, and you have this brown mapped area, and you have these contours on FEI. You can see that FEI of 0.9, 1.0, and so on. And all that we did is we take the flow pressure cataloged, published catalog range, and you do that math calculation, and it so happens that you will get these contours for FEI. So if you have a broad range, the colored, red colored range in the map, that is a efficient fan, highly efficient fan, right? You get a wide area of coverage. Whereas over here, you will see that it's a very low area of coverage. So the FEI contour is very small. And in general, I'm not being very specific. In general, forward curve fans that you see, these, you call them the squirrel cage type fans, they fall in this category, whereas the backward curved and the airfoils that you also see fall in this category. So for you to walk out of here with a perspective, sooner or later this is going to go away. But in the FEI metric, this still has a chance to be applied because there is a range still where the FEI is greater than or equal to 1. So forward curve fans indeed have their advantages, because and we'll talk more about that on the noise side of things. But from an efficiency side of things, it is not as efficient, but it does blow a lot of volume of air in a very small space, right? But it's not efficient. So you should take that away from here. So we talk a little bit about these representation of data compliance and this DOE test procedure. That is law today. Since April 29th of 2024, all fan manufacturers, like how you have appliance manufacturers like washers, dryers, they have to meet certain levels. This has been published for fans and blowers already in April 29, 2024 for the test procedure, and all of us have to comply with it. And in addition to that, the state of California also has the energy conservation rule of FEI to be greater than or equal to 1. The DOE is still working on what those levels need to be. There has been a lot of exchange between AMCA and the DOE, and at the present moment, that ruling has been stopped. Under the Biden administration, it was very active, but under the Trump administration, several regulations have been paused, and fans and blowers have also been paused. But I don't want the energy conservation standard to be confused with the test procedure, which is still law today. So any representation of data by the fan manufacturer should include certain rules, which is somewhat different. These FEI rules are somewhat different from the AMCA standards, if you're familiar with them, like 211, where you have the tolerances that you can apply in an enforcement test. This is not an enforcement test. This is how you publish your ratings in your catalogs or in your selection programs. So this is one difference is this main thing is called the tip speed rule, where the diameter of the rating or what you publish times the speed of the rating has to be greater than or equal to the diameter of the test fan times the speed of the test fan. This rule has to be followed. And the other thing is the FEI ratings that you publish has to be less than or equal to the FEI test. That's another rule that you have to follow across the published range of all fan models and sizes. That's important to note. Test procedure compliance applies to testing and ratings of all models between the range of 1 brake horsepower on the shaft, if you have a shaft rating, and an air horsepower less than 150. Air horsepower is flow times pressure on the air side power. Energy conservation standard for the California Title 20 is already in effect with FEI greater than or equal to 1. In compliance, you can only be compliant if FEI is greater than or equal to 1, along with the DOE test procedure requirements, which I have stated here. Is that very confusing or is that clear? You need to know the difference between the test and rating procedure and the energy conservation standard. And I tried to, California has both, DOE has the test and rating procedure, energy conservation standard is being discussed. FEI and code standards and regulations, that's what I say here. The test procedure of 2023 by the US Department of Energy went into effect on April 29th for all energy representations. Effective enforcement date is April 29th. For the DOE, for the energy conservation standard, they call it the NOPR. It's called the NOPR and not the final energy conservation standard. NOPR means Notice of Public Ruling. So this has been paused or withdrawn at the moment on 1/10/2025. This is hot off the press, and this is the final rule. So the final rule can be extended to 2030 and beyond. And as you can see, this is a big function of who is in government, basically, because they can pause, they can revive. But in general, at least for me, as good citizens, you have to save energy to eliminate a lot of problems in this world relating to climate change and sustainability, which is all the theme of ASHRAE. You have to be good citizens. And California has already published FEI greater than or equal to 1 for product compliance. It is complete, and the energy conservation standard is also in effect since April 29, 2024. And all the other ASHRAE standards, 90.1, which is the equipment standard. You have 189.1, which is the complete building energy efficient standard. IGCC, Green Construction Code, all these are published. Florida Building Code, some of them are complete, some of them have already taken effect, but this gives you an overview. But in general, everybody has adopted the FEI metric. Everybody wants to conserve energy, and we are on the pathway to that. Any further questions? So now Brandon will take over.
Great.
It's a whole new twist to this presentation. And go ahead, Brandon. Thank you.
Thanks, Rad. All right, good morning, everyone. How's everyone doing? Doing well? Yeah, okay. I'm exhausted, but I'm looking forward to going back home and just, propping my feet up. But before I do, we're going to talk a little bit about noise. So Rad's done an excellent job setting me up, and one thing I want to communicate today is that everything we've been talking about with fan efficiency is an indicator of the noise that the fan would produce, but it's not a guarantor. So we still have to do the analysis, work with consultants and engineers to properly select a fan that's going to meet the acoustical performance requirements on any project. And that's important because unlike fan energy or energy consumption, we don't really regulate noise and vibration in the same way. We have guidelines for best practice, and it's up to the consultants and building owners to put that as a priority, right? So really just have to kind of keep that in mind. And when we're talking about a holistic building consultation, a holistic design for buildings and wellness, we really have to keep noise in the center. And that's because if we survey our building occupants, surveys done by US Green Building Council, Well Building Institute, we find that acoustic comfort and quality are the top complaints. Brad mentioned that we spend most of our time indoors, so why are we choosing to live in these environments that just acoustically friendly? I thought it helpful to start with just kind of breaking out the two components of fan noise. They are both related, and they're both related to efficiency, but just kind of want to set the stage for what we're going to talk about. The first is a broadband noise. Let's listen to what that sounds like. And that's due to vortex shedding. As the blades move, there's a pressure gradient that builds. If that pressure gradient is constant, little noise is generated. But in reality, there is some amount of inefficiency, and as the pressure gradient breaks away from the blades, we generate that turbulence, and that turbulence can extend into the mixing zone to further create this broadband noise. Now, that was fairly loud, and maybe we don't want to listen to that level all day, but you can imagine that at a lower level, that might actually give you a sense of comfort. You might not hear your neighbor next door. It might help you just focus on work. So some amount of noise is useful. But it's this tonal noise from the blade passage frequency. Let's listen to what that sounds like. Pretty nasty, right? So every time blade moves past a point, an impulse is generated. And the repetition of that impulse creates this tone frequency. And tones are very, very annoying. There are things like the blade geometry and fan type that determine where in that frequency range it occurs and the intensity of the tone. So if we're talking about that vortex shedding noise, these are all rules of thumb, but let's start with just general guidelines. A fan is quietest near its peak efficiency point. This is a diagram that you can find in chapter 49 of the applications handbook. It's for a plenum fan. And you can see at the maximum efficiency point, our sound power, A weighted, is at its lowest point. Okay. And generally, we like to think of smaller fans as being less efficient for a variety of reasons. Typically, the faster rotational speeds have something to do with that. There's more surface roughness. There might be imperfections due to the weldments or mechanical fasteners. And there's more surface unit per volume of air that has to push through that fan. In general, we tend to like larger, slower fans if we're talking just very general guidelines for quieter design. When Rad and I discuss, he is quick to mention, though, that with large fans, especially when they are moving at slower speeds, we really have to be careful because that blade tone can dip into very, very low frequencies. Low frequencies can be very difficult to attenuate and control, so you have to kind of balance multiple factors when you're making a selection. You have to consider both the broadband and where that tone is occurring. And if we stay in the land of rules of thumb for just a moment more, again, we're talking about max efficiency as our best noise operation point. We tend to avoid the regions of the fan curve to the left, often because there can be mechanical failures that occur as you go into stall and surge regions. But it's also just happens to generate louder, low-frequency noise. Again, very difficult to control, so best to stay out of the left side of the fan curve. More often than not, in real practical designs, we tend to find ourselves to the right of optimal point, right? Because we are choosing between cost, efficiency, size. And while we don't experience the mechanical failures when we operate right of peak efficiency, there are pretty significant implications on both energy consumption and fan noise. Even if we are just slightly to the right of that maximum efficiency, you can increase power consumption by 20% and noise can be increased by 5-6 dB just to operate to the right side of that maximum efficiency. So we've given some general rules of thumb, but at the end of the day, we as consultants, we work best when we receive data from manufacturers that has been tested in accordance with some sort of procedure. Most fan data we get tends to be derived from AMCA 300, which is based on a reverberation room method. There's a reference sound source. We know how much wattage and power that generates, and we swap that reference sound source out for the fan that we're considering. There are a couple of tests. We want to look at both the overall sound, but individual paths. Depending on the fan type, we might be interested in the inlet sound, the outlet sound. And while the sound off the casing tends to be less than the outlet and inlet, it can be an aspect of the sound, and we want to make sure we consider that as well. While less common, there is AMCA 320, which is a sound intensity method. They use a probe and they scan an imaginary box around the unit, and you get similar, hopefully very close results between the two test methods. This here is a test facility. that can be used for the AMCA 300. But you can also quickly set up the fan and bring your probe in and do 322. There are pros and cons. Rod, do you want to mention anything there?
Yeah, I just wanted to add that the casing radiated noise is extremely important, not so much in the HVAC world, the breakout noise, but in the process and industrial world. Because most of the fans are ducted, and these fans make a lot of noise, like pressure blowers and things like that. So casing radiated noise, the 85 dBA environment for sound pressure at 3 feet or 5 feet is almost 99% in specifications. So casing radius, sometimes customers would want us to test in the industrial world for casing radiated noise. And also sound intensity for large fans, that is the only method available. So sound intensity, you can't really have a large fan in a reverberant room. You can do model test and then scale up the sound performance, but intensity is very, very common in large fans and big air handlers, for example.
Thanks, Rod.
Thank you.
To test every duty point would just be economically infeasible. So we generalize by testing at 5 points along the curve for a given duty point, keep the RPM constant, and the output that's important to us as acoustical consultants is that sound power level. And it's important that we get it to a resolution of 1/3 octave band. You're looking at discrete frequency bins, and that'll allow you to focus in on where that blade passage tone might be that might be obscured in a single number value. Most of the time, we then convert that 1/3 octave into octave bands that maybe consultants are most familiar with. We'll see a version of that in just another slide. Since we have these couple of points, we then extrapolate or interpolate between to scale to different operating points using known fan laws. So you see at the bottom, the bolded text there, is a logarithmic ratio between the RPM that was tested versus another operation point. And we also can scale that to different diameter sizes. And so this is what the output might look like. They've already converted those 1/3 octave bands into octave bands, starting at low frequency, going to mid and high frequencies. They've tested for 3 points of operation. Each line here represents a different point on that operation. Sometimes you might see the data converted to A-weighted sound power. That A weighting corresponds to the sensitivity of human hearing. We are less sensitive to low frequencies. And ultimately, perhaps there's a single number value. But it's important to know the context that that single number value came from all of this testing and higher resolution data. So depending on the project and if it makes sense, know that that data is there for finer tooth analysis. Great, so why do we do all that testing? Why can't we just rely on general rules of thumb? And that's because every fan is different. The type of fan, the fan geometry, and the blades all contribute to the noise characteristic of that fan. So we're going to kind of do a quick rundown of the general types of fans and their noise characteristics. So starting with FC fans, generally poor efficiency. While you can get FEI of 1, it's never going to be the top rank order in the selection if you're compared to other fan types. That said, there are pros to FC fans, like it's relatively insensitive to flow distortions. There's a wide operating range, so in variable air systems, that might be a reason to choose FC fans. There isn't necessarily a blade passage tone that you have to worry about, but low frequency noise, rumble, very, very low frequency noise can be an issue with FC fans if you're not careful. And the various aspects of FC fans that might impact the overall noise, the scroll geometry, the cutoff spacing, all of that can impact the fan. So it's important to make sure that you're getting data for the exact fan that you're looking to specify. TC 2.6 put together some nice guidelines. So depending on your outlet conditions, you might be introducing more inefficiency and more noise. It's optimal that the discharge corresponds to the direction of flow. You see that the bad geometries here, the fan is flowing in a direction that is opposite or in a different direction than the discharge condition. Right. Anytime you're changing the velocity profile, you're likely inducing inefficiencies and additional noise. So smooth, gradual transitions, those are going to be your friends. And that's not just guidelines, that is based on research projects 1219. Here we have two discharge configurations, again with flow and opposite flow. If you're looking at these graphs, anytime the line is positive or higher than 0 point, that means that this configuration is noisier than the configuration on the left. And the scale that we're looking at here is from -4 basically to 10 dB of additional noise. And we're looking at very, very low frequencies starting at 12.5 hertz all the way up to 250 hertz. Right? Some of that is even in the infrasound, things that we can't necessarily hear, but we do feel. They tested for a direct outlet, and then they tested for a couple different duct diameter conditions. So they did have a collar here before they transitioned to the elbow. So they looked at 1 duct diameter, 2 duct diameters, and then that percent D was just a fractional. I think it was something like 2.3 duct diameters. But anyways, you can see that for certain operating points, configuration 3 can add up to 10 dB at very, very low frequencies. If you don't realize that and you go to turn the fan on and you realize you have a rumble problem, it's too late to really do anything about that. Okay, now we go on to airfoil, backward inclined. This is probably going to be one of the more favorable when we were talking about fan efficiency as well as noise. There can be blade passage tones with this type of fan, but there are techniques manufacturers can change out the blade type and how they space the blades to minimize how severe that tone is. It is more sensitive to flow distortions, and there is a narrower useful operating range, so you have to select carefully. Plug and plenum fans, fairly good efficiency, right? But there is less turbulence, but that's offset by typically needing more power than a Howe centrifugal fan, so it kind of balances out to a net zero impact. Kind of just down the road, a good fan when we're talking about efficiency. ASHRAE has also done research on the effects of different mixing boxes on the inlet for plenum fans. It's 1420. You can see that when we have a baffle or a small inlet box, which might be typical, the noise generated, the additional noise as to the unhoused condition, relatively small, 2-3 dB, not all that much. However, if we get into a large and maybe more inefficient design of a box that's a half a duct diameter, you can see that as a function of airflow and velocity, you're starting to increase noise significantly up to about 8 dB. Vane axials tend to like vane axials because they have lower amplitudes at low frequencies. Again, those are the hardest to control. There are blade passage tones at mid frequencies that you have to deal with, but you can typically specify things like attenuators, internal liner, and so this fan can be a little bit easier to work with in design. However, you have to be really careful about fan surge in a vane axial. Let's go ahead and play that video. So in severe cases, there can be mechanical damage that happens to the fan blades. Really just want to avoid those regions left of the peak efficiency. The graph here on the right is the blade passage tone at 1 kilohertz. The blue is during peak efficiency, and you can see that it is a lower amplitude than the black, which is in that surge condition. And it's not just an increase in amplitude, but the level fluctuation, the that's going to increase the perceived annoyance. So for a variety of reasons, just best to avoid the left of the peak efficiency. With all that background, we're now going to present a hypothetical situation where we want to look at a couple different types of fans for the same duty point. As Rad mentioned, we need to know the airflow, the static pressure, and the density. So this is hypothetical, right? It'd be rare that we'd be looking at all these different types of fans for one application, but just if we focus on FEI and noise together, we can see how each of these fans might stack up. So we have all of the different performance metrics, and again, we're going to be looking at FEI and this A-weighted inlet sound power. And as an acoustical consultant, like I mentioned, that single number isn't all that useful, though we do see maybe we're starting to see some trends that maybe fans 1 and 5 aren't as desirable. So we would request the octave band full frequency sound data. right? And there it is. And if we apply some acoustician goggles to the data, we can see that the first, that forward curve fan, 196 dB at low frequencies, that's probably not going to be our first choice, just because it's going to be very difficult to provide noise control effectively and in a cost-effective way. Next, we look at the vane axial fan, and broadband, not so bad. However, maybe seeing this rise at mid-frequencies indicating the blade passage tone, so maybe wouldn't want to start there either. If we look at options 2 through 4, yeah, we're starting to see from an overall noise standpoint, if you remember, there may be a point or two off from each other in the A-weighted single number. But if you look at this plenum here, that sharp rise at 125 is an obvious sign that that's a blade passage tone. So again, on first pass, we probably wouldn't want to go with that selection either. Really, it's a matter of choosing between the option, the backward airfoil and the mixed flow, if we're just concerned with noise. So we thought it'd be useful to, from an efficiency standpoint, if we go back a couple slides, we can see that for fans 2 and 5, hey, we're doing pretty well for FEI. And so let's compare the two best efficient fans and see what kind of noise control might be required to deal with both of those selections. So as a consultant, going to plug in the noise levels for the fans at the top of my analysis. And then we're going to review what the mechanical engineer has designed. We're going to take into account the path from the fan to the end receiver room. Here, let's say this is a classroom, that it's designed for a noise criterion of NC30, right? That's a pretty quiet room, but not something super, super quiet like a recital hall. So we count up the number of lined elbows, how much internally lined ductwork we might have. We're going to have some takeoffs from the main ductwork too, so there will be losses there. And then as we convert from power to pressure, that's heard by the ear, hey, the backward centrifugal fan doesn't really require all that much to actually achieve NC30, right? Internal liner, a few elbows, that's pretty common in a design. But what happens if instead we pick the vane axial for a number of reasons? We can see at the higher frequencies, much louder than the backward centrifugal. And since we haven't really done anything to the path, we're going to exceed our criteria if we do nothing else. So we have to go back in and insert a 5-foot sound attenuator. That attenuator is going to have some amount of pressure drop, and that might cause the fan to become more inefficient, have to work harder. You can kind of see a little bit of a snowball effect occurring here. So just on first pass, very simple design, kind of highlights the importance of picking the right fan from the start. So as we wrap up, we can conclude that the recent regulations place greater emphasis on fan efficiency, as Rad mentioned, that generally operating point at higher efficiencies tends to result in quieter fans. But each fan has its own noise generation mechanisms, and it's insufficient to say that efficiency alone is going to guarantee that it's a quiet fan. You know, we were looking at, in all cases, the FEI was greater than 1, and we were still looking at fans that had sound levels in the high 80s, 90s, 100. So again, don't just be assured that, oh, I've got a very efficient fan, that means it's quiet. It's an indicator, not a guarantor. The best thing you can do is think holistically, choose an efficient fan, but also work with your consultants to review that fan noise data and make sure that the system is sufficient and compensates for that noise. Brad, you want to come back up? We can tackle this together.
Okay. So as part of the rules for PDH, we have to ask the questions and the audience has to answer it. Only then you get your PDH if you're a licensed engineer. So I'll take the first
Sure.
one. Energy efficiency is more important than ever. What is the industry doing right now? Anybody? Yes, sir.
Establishing standards.
Okay. That's good enough for the answer.
Yeah,
Okay.
great. Short and sweet.
FEI is another one. Yeah, the application independent metric, which is a simpler metric on knowing what the energy efficiency needs to be for a system, right? How are energy efficiency and fan noise related? Anybody?
Yep.
Turbulence. Yeah, it creates turbulence. And what else? So turbulence is related to what kind of noise that Brandon spoke about? Broadband,
Yep.
right? Broadband. And what is the other component?
Great.
Which is the
Yeah.
pure tone. The pure tone, yeah.
Can quiet fans be selected based on energy efficiency alone?
Come on, guys, you guys were all awake.
No.
Honestly speaking, no, and I think also the question why I came here is not answered up to now. And this is also related to the third question. Because I think that you left out one really important component, which means is the motor.
Uh-huh.
If you have a low RPM, the motor is the dominant noise factor.
Right.
And if you're only working on the turbulence and on the airflow noise, it does not affect anything if the motor is the dominant factor on this.
That's true.
And so, what you say is everything is right, but it's not the complete story. As far as I know.
That's true. Yeah, we kind of left out the motor part because as long as in general, motor efficiencies are very high, right? 95%, 90%. In general, if you're picking one and operating it properly, right?
Depends on the motor.
But you are right. If you use a drive and you slow it down, the tone generated by the motor, the whining noise that you hear can be extremely annoying. It is kind of, Brandon, I'll let you answer the difference between the fan blade pass tone noise versus the motor whining noise. Do you want to elaborate on that?
Oh, sure. Yeah, I mean, the fan tends to be either low or mid frequency. From my experience, the motor tone is very, very high pitched, and depending on where that is located can be also equally difficult to attenuate. There's also a structure component, so if it happens to get into the building structure, again, it'll travel very efficiently, and so it has to be attenuated at the source. You are identifying a gap in terms of the regulation standardization. I'm not aware of a way to test fan motor noise, at least to the same degree as fans, yes.
Yeah, but if you are talking about fan efficiency index, he said also the motor is included into this efficiency.
Right.
And if you are talking about now only about noise, you are only talking about the broadband noise and not about the motor noise. And so I think you are not touching the complete picture.
Right. So what you're basically saying is the fan efficiency energy index today, the induction motor or the regulated motor has equations for drive and for the motor, which you can combine with the shaft to air dynamometer test and create the wire to air efficiency. You are correct. There is also, you can also have a mechanism by including, if you're doing a wire to air test, if you do a reverberant test on the motor, drive and the fan, everything is included in the noise, right? Everything. So we will, if it's a tested fan with noise, we can provide that, you are correct, to the acoustic consultant. And one of the questions they should be asking is motor noise included in your ratings? Because the wire to air pathway allows you to do a calculation or a test only for efficiency right now. But if the acoustic consultant is knowledgeable enough, he's going to say, okay, when you did the testing, did you also do a test with the motor or not? And if we have done the test with the motor, we can provide that to them.
And you must know what is the dominant noise source.
Oh, yeah.
Yes, I agree. Good points, yeah.
What do you mean high efficiency motor and low efficiency?
What do you mean by high efficiency motor?
High efficiency motor, low efficiency.
Are you asking me?
No, I'm asking.
Well, motors in general, right? Motors in general at the selection point induction motors are about 90 to 95% nominal efficiency at full load. As you decrease the load, the efficiency drops, and accordingly, you can have the broadband noise could go up, and also the whines in the motor can go up. And when you couple it with a drive, it gets exacerbated even more, right, at lower speeds. At lower speeds, the blade tone can get prominent. It can get very loud. The whine can get, so which is the dominant tone?
Right.
They look at that. At what frequency is the tone? They look at that. So at the end of the day, they have to attenuate all that. They have to control that noise. So in terms of efficiency of the motor, they're all very efficient. The bulk of the problem is the fan. Fan efficiencies can range at 60, 70% in some instances.
So ECM motor is high efficiency, right?
In general, EC motors are higher efficiency. They have the combination of the motor and drive. There are other features of it which are extremely useful. You don't have to bring in all the wiring separately for the drive, for the motor. Everything is self-contained, but it has its limits. You can go only up to maybe 20 horsepower on the EC motor, maybe 25, something like that. If you want a bigger fan, you have to go to the induction motor. You don't have a choice. These days, fan arrays are becoming very popular. Where you can have multiple motors in an array in the HVAC world, but in a process world, that's not going to work. You need to have the right fan with a high efficiency. Yeah, they go into, they are in power generation stations and they consume a lot of power, sometimes thousands of horsepower. So that's it.
Yeah. Appreciate your time. Thank you.
Thank you very much. We are right on time. Appreciate it.